Okay, so welcome, congratulations for getting through the lecture material for Math 152. Well done on getting this far. We are now at the final stage. This is the final lecture for the class, which is the review for the final exam. So I'm Ben Adcock, you have me again for this lecture, and I'm going to be taking you through this material here. So there's some preamble here about the material that's going to be tested on the exam, in particular what we are going to require you to know and what we don't require you to know, and the balance of the exam itself. Please look carefully through this material. I'm not going to go through it now myself, but please take the time to look carefully through it. And if you have any questions about what you need to know, check these pages here first. So, with that out of the way, this review class, we're going to go through a series of questions, and you can think of these questions as sample exam questions for the final exam. So they should be the same flavor as the questions to expect in the final itself. There are answers at the back of these notes, but we're going to be going through these questions and working out the solutions in full detail. Okay, so we're going to start with what is the bread and butter of this course, which is calculating integrals. Okay. So question one here, we have two integrals. The first one is a definite integral. It's the integral of x plus 1 divided by x squared plus 2x minus 3. And when you look at this integral, hopefully by now you recognize fairly quickly that this is the type of integral that you want to try and solve using partial fractions. So first let's factorize the denominator. So x squared plus 2x minus 3. If you take a moment to think about it, you'll work out that one of the factors is x equals 1, and then from that you can easily find that the other factor is x equals negative 3. Okay, so we can factorize this quadratic as x minus 1 times x plus 3. So now we recognize that our integrand is a rational function of x, and the degree of the denominator is 1, and the degree of the numerator is 1, the degree of the denominator is 2, so therefore the degree of the numerator is less than the degree of the denominator, so therefore we can immediately write down the form of its partial fraction expansion, since we've also factorized its denominator. So this takes the form a divided by x minus 1 plus b divided by x plus 3. A and b are constants. So our next step is to find the constants a and b. So the first thing we do for this is we multiply up. And if we multiply up on both sides, we get x plus 1 is equal to a times by x plus 3 plus b times by x minus 1. And now let's compare coefficients. So the constant coefficient, on the left-hand side I have 1, and on the right-hand side I have 3a minus b. And for the x coefficient, on the left-hand side I have 1, and on the right-hand side I have a plus b. So this is a system of two equations for two unknowns, a and b. And if you solve this system with a couple of steps of algebra, you'll find out that a is equal to 1/2 and b is equal to 1/2. So, therefore, the integral that we're trying to calculate is the integral from 2 to 6 of x plus 1 divided by x squared plus 2x minus 3 dx. We can write this as 1/2 times the integral from 2 to 6 of 1 divided by x minus 1 plus 1 divided by x plus 3 dx. And that 1/2 is just coming from the fact that both a and b are equal to 1/2 in our partial fraction expansion here, as we just calculated. So now we can integrate both terms. So the first term is ln absolute value of x minus 1. The second term is ln absolute value of x plus 3. And all this is evaluated at the limits of integration. And if we evaluate at the limits, then we get 1/2 ln of 5 plus ln of 9 minus ln 1 minus ln 5. So the ln 5's cancel, ln 1 is equal to 0, so we're left with 1/2 ln 9, and this reduces to ln 3, okay, because 9 is equal to 3 squared. So there we go. That question took you through integration of rational functions using partial fractions, and as hopefully you all know by now, the mechanism of how we do this is to first work out the partial fraction expansion of the integrand, solving for the coefficients as we did here. Then we end up with terms like this in this example, which we can integrate using the natural logarithm. Okay, let's move on to the second example. So if I scroll back up, here we are asked to evaluate the indefinite integral of e to the x divided by e to the 2x plus 2e to the x plus 2 dx. So I am going to here, the first thing I'm going to do here is I'm going to write the denominator as e to the x plus 1 all squared plus 1. And you might just want to check why this is correct. So if you expand this, you get e to the x squared plus 2e to the x plus 1 plus 1. And then notice that e to the x squared is equal to e to the 2x. And then I have 2e to the x plus 2. Okay, so this is correct. So now what I'm going to do is I'm going to use a substitution. U is equal to e to the x plus 1. So if I use this substitution, then du is equal to e to the x dx. So therefore my integral, because I had an e to the x dx as my denominator, this becomes du. And because of the way I factorized my numerator, let me back up. Because I have an e to the x on my numerator, then my e to the x dx just becomes a du. And then because I have factorized my denominator in this form, my denominator becomes u squared plus 1. So I know how to integrate this. 1 over u squared plus 1 is the derivative of arctan u. So this is equal to arctan u plus an arbitrary constant. And then finally, I substitute back for x. So my final answer is arctan of e to the x plus 1 or plus an arbitrary constant c. So just one thing to explain here. So we did this integral by substitution. Following the general principle of substitution, we chose the substitution to get rid of the unpleasant term in the integral, or in the integrand, which was e to the x in this case. You might be wondering why I didn't take the substitution just to be e to the x. I could have done. If you had done that, then you would have ended up with an integral where you probably had to do another substitution in order to finally solve it. Doing this substitution here, I've essentially combined those two substitutions into one step, just to make things a little bit more efficient. Okay, Let's move on to part C. So we have one final integral to calculate in this first question, and this is the integral of e to the t to the 1/3. Okay, so this is the exponential of t to the 1/3 power. And this is an indefinite integral as before. So, following the general principle, we're going to do this by substitution. And we're going to set z to be the unpleasant term in our integrand, which is the cube root of t. So this gives me dz is equal to 1/3 t to the negative 2/3 dt. And therefore, if I rearrange this, I get dt is equal to 3 t to the 2/3 dz. And now I can rewrite this in terms of z as 3z squared dz. So therefore my integral is equal to e to the z, here's my, using my substitution, times by dt, which is equal to 3z squared dz. So now this is an integral. I have a polynomial term times an exponential. So now what we're going to do to calculate this is we're going to integrate by parts. Okay. So to integrate by this by parts, I'm going to set my u to be 3z squared. So therefore du is equal to 6z. And I set my dv to be equal to e to the z dz. So therefore v is equal to e to the z. Why do we do it in this way? Hopefully you're all familiar with this now. We're following the general idea that when we integrate by parts, we want to take u so that when we differentiate, our du becomes simpler. So here we go from z squared to z up to constants, and where when we integrate v, things get no more complicated. So here we go from e to the z to e to the z. So now we use the integration by parts formula, so we will get uv, so that's 3z squared e to the z, minus v du. So du is 6z dz, and v is e to the z, so I get the integral of 6z e to the z. Okay, so how are we going to do the next step? We're going to do this by parts again. So for this second integral, let's take u to be equal to 6z. So then du is equal to 6 dz. And let's take v is equal to e to the z. Dv is equal to e to the z dz. So therefore v is equal to e to the z. So I'm going to move down here. So now I get 3z squared e to the z minus, okay, so now I have my by parts formula, so that's uv, which is 6z e to the z, minus the integral of v du, so v is, du is 6 dz, and v is e to the z, so I get 6 e to the z dz. So what do I have? I have 3z squared e to the z minus 6z e to the z plus the integral of 6 e to the z, which is just 6 e to the z plus an arbitrary constant. Okay, so the final thing we need to do here is just substitute z for t. So let's go ahead and do that. I'm going to factorize out a factor of 3 here as well. And I'll also factor out the e to the z as well. So the first term we have now is z squared. So this is, because z is the cube root of t, so this is t to the 2/3. Now I have minus 6z. So I pulled out a 3 already, so I'm going to get 2 t to the 1/3. And then my final term is just 6. So I'm going to get 2 here. And then I have my e to the z outside, so I'll get e to the t to the 1/3 plus an arbitrary constant. And that's our solution. So in this example here, we first did the substitution to get rid of the unpleasant term in the integral, which is this cube root of t. Then we ended up with an integral that was of the form of a polynomial times an exponential. And as you should know now, because you've seen a bunch of examples on this, for this kind of integral, we can solve it by integrating by parts one or more times depending on the degree of the polynomial. So here the polynomial was a quadratic, so we did 2 integrations by parts. Okay, let's move on from integration and let's tackle a differential equation. So in question 2 here, we are asked to find the solution to the following initial value problem. So the differential equation is dy by dx is equal to y cosine x divided by 1 plus y squared. And the initial condition is that when x is equal to 0, y is equal to 1. And we're told here that we can leave our solution in explicit form. So we'll talk about that in a minute as well. So the first thing we recognize here is that this is a separable differential equation. Our function on the right-hand side here separates into a function of y multiplied by a function of x. So what this means is that I can move my y terms over to the left-hand side. So I get a 1 plus y squared divided by y dy. And then I move my x terms over to the right-hand side, or I keep them on the right-hand side for the cosine x. I move my dx over to the right-hand side, and now I integrate both sides. So on the left-hand side, I've got the integral of 1 plus y squared divided by y. And on the right-hand side, I've got the integral of cosine x dx. So the left-hand side, let's expand the numerator. So I get 1 over y plus y dy. And then on the right-hand side, we can integrate this right away, and we can write this as sine x plus an arbitrary constant. Now let's integrate the left-hand side. So I get ln of the absolute value of y plus 1/2 y squared is equal to my right-hand side, which is sine x plus an arbitrary constant. Of course, because we already have an arbitrary constant on our right-hand side, we don't need a second arbitrary constant on our left-hand side. Okay, so this is the solution of the differential equation. So let's apply the initial condition, which is y of 0 equals 1. And what this is going to do is this is going to determine the constant for us. So if I plug that in to the equation above, I'm going to get ln of absolute value of 1 plus 1/2 times by 1 squared is equal to sine 0 plus c. Ln 1 is equal to 0, sine 0 is equal to 0. So this is going to tell me that 1/2 is equal to c. Okay. So we've determined our constant. That's what the initial condition does for us. It determines the constant in the general solution of the differential equation. So therefore, the solution of the initial value problem is ln absolute value of y plus 1/2 y squared is equal to sine x plus 1/2. And that's the form that we leave this in. This is what we call the implicit form. As we discussed in lectures, if you look at this equation, so normally we would try and solve explicitly for y. That would give us the explicit form of the solution. But if you look at this equation here, it's not clear, and in fact it's not possible to solve for y explicitly in terms of x, so we leave the solution in this form. Okay, and this is, as I was saying, this is what we call the implicit form of the solution. Okay, so this is the basic idea of solving separable differential equations. So whenever you have a separable differential equation, you move all your y terms over to one side, your x terms over to the other side, you integrate both sides. That gives you the general solution of the differential equation, as we're getting here. Then you apply your initial condition to get the constant. And depending on what the question tells you to do, you either solve explicitly for y in terms of x, or if it says to do so, you leave your solution in the implicit form, as we did here. Okay, let's move on to our next question. And so in the next couple of questions, we're going to be talking about areas and lengths of curves and volumes. So in this first question, we're asked to determine the length of the following curve. So this is a curve given as y is equal to the integral of the square root of t squared minus 1 dt from 1 to x. Okay? And we're asked to find the length of this curve for x between 1 and 4. Okay? So the important point to make here is that this question might look like it's stated in a slightly obscure way. Just keep in mind that this is a function of x. Okay? It's an integral where the upper limit is equal to x, so therefore that defines a function of x. Okay. So how do we find the length of the curve? Well, if you go back to section 8.1 of the course, you'll find the formula there that says the arc length of a curve y equals f of x from x equals a to x equals b is given by the following formula. So it's the integral from a to b of the square root of 1 plus f primed of x all squared dx. So now what we need to do is apply this formula. So going back to our equation here, this is now our f of x. Okay? So the first thing that we notice is we actually don't need to find f of x explicitly in terms of x in order to apply the arc length formula. Actually, we just need to find its first derivative, f prime of x. So what we can do now is we can use the fundamental theorem of calculus. So by the fundamental theorem of calculus, f primed of x, well, f of x is defined where the x dependence is the upper limit of integration. So by the fundamental theorem of calculus, f primed of x is equal to the integrand evaluated at x. So it's just x squared minus 1. So now we can go ahead and calculate its arc length. So the arc length is equal to the integral from a to b. So in our case, we're told that the a is 1 and the b is 4. So that's coming from here. And now we have the square root of 1 plus f primed of x squared. So if I square f primed of x, I'll get x squared minus 1 dx. My 1's cancel. So I have the integral of the square root of x squared. The square root of x squared is equal to x dx. So this is the integral from 1 to, So this is the integral of x. So this is equal to 1/2 x squared evaluated at 1 and 4. And this is equal to 16 over 2 minus 1 over 2, which is equal to 15 divided by 2. And that's our answer. So arc length, the thing that we have to keep in mind is the arc length formula here. And then what you also saw in this question was a refresher on the fundamental theorem of calculus. So when you have a function that's defined like this, okay, in terms of an integral, where the x is the upper limit of the integral, then the derivative of that function is equal to the integrand evaluated at x. Okay, let's move on. And now let's look at another question involving the application of integrals to calculating things like lengths and areas. So in this question, question 4, we are going to study the following curve. So this is known as the Archimedean spiral, and this is the curve that's defined parametrically by the following equations. So x is t cosine t, y is t sine t, and we're looking at this curve for t between 0 and 4. So the first thing we're asked to do in part A is to find the length of this curve. And so if you look back through your notes, you'll realize that in section 10.2 of the lectures, we studied various formulae for arc lengths and areas and things like that of curves that were defined parametrically. So in particular for arc length, we found the following. So the arc length of a parametric curve so parametric curve has the general formula x equals f of t, y equals g of t. And suppose the parametric curve is defined for t between alpha and beta. Then the formula for its arc length is that L is equal to the integral from alpha to beta of the square root of f prime of t all squared plus g prime of t all squared dt. So in our case, f of t is t cos t, g of t is t sine t, and alpha is 0 and beta is 2 pi. So therefore L is equal to the integral from 0 to 2 pi of the square root of f prime of t, so that's cos t minus t sine t all squared, plus g prime of t, which is sine t plus t cos t all squared dt. And now let's expand these brackets out. So if I expand the first bracket, I get cos squared t minus 2t cos t sine t plus t squared sine squared t. And now if I expand the second bracket out, I get sine squared t plus 2t cos t sine t plus t squared cos squared t. And we're taking the square root of this, so I've written this as raised to the 1/2 power dt. And what we notice here is, well, first of all, the cross terms cancel. So we have a 2t cosine t and a negative 2t cosine t, 2t cosine t sine t that cancels with a negative 2t cosine t sine t. Moreover, we can make one further simplification using the fact that cosine squared t plus sine squared t is equal to 1. So what we get is the integral from 0 to 2 pi. So the first thing we do is we match this cos squared t with this sine squared t to get 1. And then we match the t squared sine squared t with the t squared cosine squared t to get t squared. This is equal to the integral. So now we get our integrand is 1 plus t squared raised to the 1/2 power. So now we need to calculate this integral, and fortunately, because otherwise it's not a particularly pleasant integral to calculate, we are told that the indefinite integral of the square root of t squared plus 1 is given by this formula up here. So this is equal to 1/2 t times the square root of t squared plus 1 plus ln t times the square root of t squared plus 1. And we evaluate this at 0 and 2 pi. So to complete this, we just need to evaluate this at the limits. So we're going to get 2 pi, or 1/2 times 2 pi, 4 pi squared plus 1, plus ln of 2 pi plus the square root of 4 pi squared plus 1. And then at the lower limit, we'll get minus 0, minus ln of 0 plus the square root of 1. And notice that this term here gives us 0. So what we're left with is pi times the square root of 4 pi squared plus 1 plus 1/2 ln 2 pi plus the square root of 4 pi squared plus 1. And that's our solution. Okay, so the main thing in this question was to recognize that we had a parametric curve, and then to remember and recognize the formula for the arc length of a parametric curve, which is given by this expression here. Okay, so let's move on to the second part. So here is our curve again, and now in this part B we're asked to set up, but we're not asked to evaluate, we're just asked to set up the integral for the area of the region bounded by the Archimedean spiral and the x-axis. Okay, so this is the region that's been shaded for us in this figure here. So what we want to do here is we would like to figure out this point. We'd like to figure out the value of t that corresponds to this point. And we'll see why I'm doing this in a second. Okay. So this point lies on the x-axis. So let's find the x-intercepts. So to find the x-intercepts, we solve for y equals 0. So that's equivalent to saying that t sine t is equal to 0. And therefore the x-intercepts occur at t equals 0, t equals pi, and t equals 2 pi. Remember that t goes between 0 and 2 pi in this question. So the point here where t is equal to 0 is the origin. This is the point where t is equal to pi. And this is the point where t is equal to 2 pi. Okay? And if you weren't sure of that, you could just plug the different values of t into your expression for your x-coordinate, just to check that. Now, once we know these, okay, then what we're saying is that this area, okay, so the area in grey, is the area, well, okay, so it is the area underneath the parametric curve between t equals pi and t equals 2 pi. Okay, so technically, because the curve lies under the x-axis here, it's the area between the curve and the x-axis, so we're going to have to include a negative sign. But the main point is we recognize this as an area under a curve. So now what we can do is we can go back to section 10.2 of the lectures, and the specific result here that we need says that the area under a parametric curve is the integral from alpha to beta of g of t f primed of t dt. Okay, so if you have a parametric curve written in this general form that I've written here on the previous page, the area under that curve is given by this formula here. So in our case, the area that we're interested in is going to be negative the integral from pi to 2 pi of g of t, which is t sine t, times by f primed of t, which is cosine t minus t sine t dt. So that's our answer. So let me just be clear on a couple of things here. So the g of t, that's giving us the t sine t here. The f primed of t, so remember that f of t in our setup, f of t was equal to t cosine t. G of t is t sine t. The alpha and beta come from these values here that we determined give us the endpoints of our curve. And then the one final thing is this negative sign here. And this is since we want the area, or since we want a positive area. Okay, and that's it. Final part, part C. Again, we're asked to set up an integral, but we're not asked to evaluate it. What we're asked in this part is to set up the integral for the area of the surface of revolution obtained by rotating the part of the spiral in the second quadrant about the x-axis. Okay. So let's go up to the diagram here and let me use the red color. So we're asked for the part of the spiral that's in the second quadrant. So that's this area here. So let me draw a box around this. And there you go. And so now we want the surface of revolution obtained by rotating this area about the x-axis. Okay, so we're going to rotate around the x-axis here. So the first thing we need to do is we need to find this point here. Okay. Why do we need to do that? Because we want to find the t values that give us this region of the curve. Okay. So let's find the y-intercepts. So these are going to be given by t cosine t equals 0. So therefore t is equal to 0, pi by 2, or 3 pi by 2. And if you do a couple of calculations to find the y values, this is going to be when t is pi by 2, and this is when t is 3 pi by 2. So the value we're interested in is t equals pi by 2, rather than the t equals 3 pi by 2 value. Okay, so again, we go back to section 10.2. Section 10.2 tells you that if g of t is greater than or equal to 0 for t between alpha and beta, then the surface of revolution obtained by rotating around the x-axis is equal to the integral from alpha to beta of 2 pi g of t times by the square root of f primed of t all squared plus g primed of t all squared dt. So in our case, our alpha is 0, our alpha is pi by 2, our beta is pi. So we just go up to the diagram here. We are integrating this curve here. So we start at pi by 2 and we end at t equals pi. So we have the integral from pi by 2 to pi of 2 pi g of t. So that's 2 pi t sine t times by the square root of f prime squared plus g prime squared. But we already worked out what this was in part A. That just reduced to 1 plus t squared. So this final bit here, this is as we found in part A. So there we go. That's our integral. So again, we relied on a formula from section 10.2 of the material. Once we had that formula, the main thing that we had to do was to work out the lower and upper values of t. Okay, so in this case, we recognize them as corresponding to this point and this point, and we found t is pi by 2 and t equals pi. Okay, so let's move on, and now we're going to move on to calculating some volumes. And I am struggling to find my notes. Okay, here are my notes. So question 5, we are interested in the following curve. So the curve y equals x squared times x minus 2. So the curve is plotted here. Obviously it intercepts the x-axis at x equals 0 and x equals 2. And we're interested in the region that lies between this curve and the x-axis. So this is this region here. So in part A, we are asked to use the method of cylindrical shells to compute the exact value for the volume of the solid of revolution obtained by rotating r around the y-axis. Okay. So in part A, we're going to rotate around this way. And we're also asked to draw a typical cylindrical shell. So let's do that. So let's put the origin here. This is the point 1, this is the point 2, this is -1, -2. So first thing I'm going to do is redraw the curve. And first thing I'm going to do is remember to change my pen setting so I can draw the curve properly. And there we go. Okay, so that's our curve, and I've drawn its reflection as well through our axis of rotation, which is in dash here. And so this is the axis we're rotating around. And now we are going to use cylindrical shells to calculate the volume of the solid of revolution. So let's take a typical shell. So here's a shell. This is the vertical of a shell, and this is going to be the shell at x. Let me draw its mirror image here. And so our shell looks something like this. Okay, so that's our shell. Yeah. And this is the shell at x. And so you'll remember, I should have already pointed this out already, that this question is based on material that you saw in section 6.3 of the lectures. And so you'll remember for the method of cylindrical shells, you need to find the area of this shell. And in order to do that, you need to find the radius of the shell. So in this case, the radius of our shell is r. Well, this is just equal to x in this case. Okay. We're rotating around the y-axis, so the x equals 0 line. So our radius is equal to our x value. Next, we need the height of the shell. So the height of the shell is this here. Okay. Well, we know this point here. This is the point on the curve corresponding to x. So the height is going to be negative. So because our curve lives below the x-axis, the height here, so this distance is going to be negative x squared times x minus 2. Okay, so remember the height should always be a positive quantity, obviously. So therefore the area of our cylindrical shell is 2 pi times the radius times the height, which is 2 pi times x times by x squared times 2 minus x. So I'm going to write this as 2 pi times 2x cubed minus x to the 4. So now we know the area of our shell. The volume of the solid of revolution is given by the integral from the limits of x, which is 0 and 2, of this area. So that's 2 pi times 2x cubed minus x to the 4 dx. So that's equal to 2 pi times by, if I integrate 2x cubed, I get x to the 4 divided by 2, minus, if I integrate x to the 4, I get x to the 5 divided by 5, evaluated at 0 and 2. And this gives us 2 pi, 2 to the 4 is 16, so I have 8. 2 to the 5 is 32, so I have 32 divided by 5. And so this is 2 times pi times 8 minus 32 over 5, which I guess is 2 pi times by 8 over 5, which gives me 16 pi divided by 5. Okay, so that was the answer to part A. And I think before I do any more discussion on this, I'm going to look at part B. So, in part B, you're asked to find the integral representing the solid of revolution obtained by rotating the same region around, rather than around the y-axis, around the line x equals 3. Okay. And you're asked in this case to draw a diagram, which we'll do, and then determine and indicate which method you're using, the washer method or the shell method. So, let me draw another picture here. So, here's 0, this is the point 3, 2, 1, 4, 5, 6. Let me draw in our original curve. So that's our curve, and this is our axis of rotation. So we're rotating around the axis x equals 3. So let me draw the mirror image of this curve. So we get something like that. And now we want to set up the integral. So what we're going to do is, so we're asked to whether we should use the shell method or the washer method. And what you notice here is because we're rotating around, because we've given the curve in the form y is equal to a function of x, and because we're rotating around a vertical axis, we're going to use the shell method. So let's draw a typical shell. So let's take a point X here. So here's X, here's its mirror image. Here's my shell. So we use the shell method again. And so again, we calculate the radius. So the radius is this distance here. And so what's different now is that the radius is 3 minus x rather than x. The height is the same. The height is negative x squared times x minus 2. So therefore our volume is equal to the integral from 0 to 2 of 2 pi times 3 minus x times x squared times 2 minus x dx. Again, we're just using the same expression for the area of the cylinder, and then we integrate the area of the cylinder. Okay, so the main things to take away from this question is how to set up the shell method, and then remember that in order to use the shell method, you work out the area of the shell, which is 2 pi r h, where r is the radius of the shell. So in this case, it's given by this. In this case, it's given by this. Times by the height. So that's this thing here in both cases. And then your integral is just the integral from your limits in x of 2 pi times r times h. In the second part of the question, we were asked to choose whether or not to use the shell method or the washer method. So if we were to try to use the washer method here, we would draw a washer that looks something like this. But in order to use the washer method, we'd have to find these points, as functions of y. That would not be so straightforward. So in general, you want to use the shell method for this kind of question because your axis of rotation is a vertical axis and you're given the curve where y is a function of x. If the curve was given as x is a function of y, then we want to use the washer method instead. Okay, let's move on and let's talk about series. So now we're going to move on, and for the next few questions, we're going to focus on what you've been doing in the last chapter of the material in the textbook. So this is chapter 11. This is all about series. So in question 6 here, we're asked to determine whether or not the following series are convergent or divergent. And we're asked to state which test we're using to determine this, the answer to this question. So let's get started. So for our first series, the general term of the series is square root n squared minus 1 divided by n cubed plus 1. So what I'm going to use here is the comparison test. So the comparison test you saw in section 11.4. And notice that the square root of n squared minus 1 is less than or equal to the square root of n squared, which is equal to n. And that n cubed plus 1 is greater than or equal to n cubed. So both these things combined together tell me that n squared minus 1 divided by n cubed plus 1, which is the general term of my series, this is less than or equal to n divided by n cubed, which is equal to 1 over n squared. So the general term in my series is bounded above by the quantity 1 over n squared. But I know that the sum from n equals 1 to infinity of 1 over n squared converges. Therefore, by the comparison test, we deduce that the series that we're interested in also converges. So remember, the comparisons test says that if you have a series of non-negative terms, so all these terms are non-negative, and they're bounded above by another set of terms for which the corresponding series converges, then the original series must converge as well. Okay, so that was using the comparison test. Now let's move on to our second series. So this series contains powers of n and factorials, and so generally a good thing to try for this kind of series is to use the ratio test. So let's use the ratio test. So this is what was introduced in section 11.6. So in the ratio test, we look at the limit of the absolute value of the ratio of the n plus 1th and the nth term of the sequence. So an plus 1 divided by an. So in our case, this is the limit as n tends to infinity of n plus 1 factorial divided by 2 to the n plus 1 times by n plus 3 factorial. So that's the n plus 1th term of our sequence, divided by the nth term, which is n factorial divided by 2 to the n times n plus 2 factorial. And of course, all the terms here are positive, so we can get rid of the absolute values. Okay, so let's simplify this. But before we simplify this, let's write this in a slightly less unpleasant way. So let's write this as n plus 1 factorial times 2 to the n plus 1 times n plus 3 factorial times by 2 to the n times n plus 2 factorial, all divided by n factorial. And now what we can do is we can simplify our terms. So my n factorial is going to cancel with my n plus 1 factorial and give me a factor of n plus 1 here. My n plus 2 factorial is going to cancel with my n plus 3 factorial and give me a factor of n plus 3 here. My 2 to the n is going to cancel with my 2 to the n plus 1 and give me a factor of 2. So what I'm left with is I'm left with the limit as n tends to infinity of n plus 1 divided by 2 times n plus 3. Well, on my numerator I have n plus 1, on my denominator I have n plus 3. If I take the limit of their ratio, that's going to give me 1. I have this factor of 2 here sitting around in my denominator, so what I deduce is this limit is equal to 1/2. I'm going to rewrite this here because it didn't come out very well. So the numerator is n plus 1. So I've determined the limit of the ratio of the absolute values of my terms in my sequence is 1/2. This is less than 1, so therefore my series converges by the ratio test. Okay, let's move on to part C. So part C, we have a series where the general term is -1 to the n times ln n divided by n. So this is a type of alternating series. So recall that an alternating series has the form -1 to the n bn. Okay. So in our case, bn is equal to ln n divided by n. And I should be clear here, it's an alternating series if the bn are greater than or equal to 0. So in our case, the terms are ln n divided by n. These are certainly greater than or equal to 0. Also, bn is greater than or equal to bn plus 1, so these terms are decreasing. And the limit as n tends to infinity of bn is equal to 0. So therefore, the series converges by the alternating series test. So remember, for the alternating series test, you need to have a series where the sign of the terms is alternating. So it should look something like, this, -1 to the n times bn, where bn is greater than or equal to 0. And then the condition of the test are that the terms are decreasing and that their limit is equal to 0. Both of these properties are satisfied in our case. So therefore, our series converges by this test. Okay, let's move on to another question about series. And now we're going to look at power series. So, for each of the following series, we are asked to determine the radius of convergence and the interval of convergence. So remember that a power series is a series that involves powers of x raised to the nth term of the series involves something like x to the n, or x minus 2 to the n, or in general x minus some number a to the n. Okay. So we want to determine the radius of convergence of a power series. So recall that the radius of convergence, this means that for all values of x less than some number r, the series should converge, and that for some values of x, or at least one value of x greater than r, the series diverges. Okay. So the way in which we're going to do this is by using the ratio test. So again, we have a power series. Generally, the ratio test is useful for determining series that involve powers of n, as I already said. So that's what we're going to use here. And so again, we look at the limit of absolute value of an plus 1 divided by an. So this is the limit as n tends to infinity of absolute value of -1 to the n plus 1 times x to the n plus 1 divided by n plus 1 squared times 7 to the n plus 1, all divided by -1 to the n times by x to the n times by n squared times 7 to the n. Sorry, divided by n squared times 7 to the n. Okay, let's cancel our terms. So -1 to the n is going to cancel with this and give us -1. X to the n is going to cancel with x to the n plus 1 and give us x. 7 to the n is going to cancel with 7 to the n plus 1 and give us 7. And so what we're going to be left with is the limit as n tends to infinity of, well, first of all, our -1, we're going to take the absolute value, so we don't need to worry about that. So we're going to get absolute value of x divided by n plus 1 squared times 7. And then this n squared that's sitting down here is going to come up in our numerator here. So we'll get n squared. Okay, so now in our numerator we have n squared. In our denominator we have n plus 1 squared. Take the limit as n tends to infinity. That ratio is going to tend to 1. So we're left with the absolute value of x divided by 7. So, therefore, the series converges for absolute value of x less than 7. Okay? So this ratio, absolute value of x divided by 7 is strictly less than 1 whenever x is less than 7 in absolute value. So the ratio test tells us that that's when the series will converge then. And now let's consider what happens when x is bigger than 7. So suppose the value of x is bigger than 7. Then the terms of the series, negative 1 to the n, x to the n divided by n squared, 7 to the n, do not tend to 0 as n tends to infinity. So therefore, the series does not converge. And therefore, we deduce that the radius of convergence is equal to 7. So that tells us the radius of convergence. Now we're asked to find the interval of convergence as well. So what about I? So the only thing that we need to do, we've determined that the series diverges when x is bigger than 7 or less than negative 7. We've determined it converges when x is less than 7, bigger than negative 7. The only thing we need to do is look at what happens when x is either equal to plus 7 or negative 7. So, if x equals 7, plug that into our series, and what does it become? It becomes the series negative 1 to the n divided by n squared, which converges. And if x is equal to negative 7, then our series becomes 1 over n squared, which also converges. So therefore, our interval of convergence is the closed interval from negative 7 to 7. Okay, so it contains both x equals negative 7 and x equals positive 7. So remember, going back to the ratio test here, keep in mind here that the ratio test tells you nothing when the ratio is equal to 1, and that's exactly these two cases here where x is equal to plus 7 or negative 7. For those, we have to look in a different way in order to determine whether or not the series converges or diverges. Okay, let's move on to example B. So example B, problem B, or part B, we're asked to determine the convergence or the radius convergence of this power series. And again, we'll do this by the ratio test. So let's look at lim n tends to infinity, absolute value of an plus 1 divided by an. This is lim n tends to infinity of 2 to the n plus 1, absolute value of x minus 2 to the n plus 1, divided by n plus 3 factorial, all divided by 2 to the n, absolute value of x minus 2 to the n, divided by n plus 2 factorial. And now let's cancel our terms. So here we get 2 to the n, cancels with 2 to the n plus 1 and gives us 2. X minus 2 to the n cancels with x minus 2 to the n plus 1, which gives us absolute value of x minus 2. And n plus 2 factorial cancels with n plus 3 factorial and gives us n plus 3. And we are left with the limit as n tends to infinity of 2 times x minus 2 in absolute value divided by n plus 3, and that limit is equal to 0. So therefore, since the limit is equal to 0, and this is for any x, the radius of convergence is actually infinity and the interval of convergence is the whole real line. So it's negative infinity to infinity. So the ratio test gives us a limit here that's equal to 0. This is true for any x. So therefore the ratio test tells us that we converge for any x, which means our radius convergence is infinity and our interval of convergence is the interval from negative infinity to infinity. Okay, so to take away from this question, if you're asked to determine convergence of power series and find the radius of convergence and the interval of convergence, generally using the ratio test is the standard way to go about this. This will normally tell you the radius, but you should also check what happens outside of the value that you get from the ratio test. And then to determine the interval, as we did in part A here, you need to look at what happens at the endpoints. So where the ratio test is not telling you anything because the ratio is equal to 1. Okay. But as part B is saying, there are examples where the ratio test will tell you everything because the radius of convergence is actually infinity. Okay, let's move on. So now we move on to a different question about series, and here we're looking at convergence of series, and here we're asked to prove that the following series, so the series from n equals 2 to infinity of 1 divided by n times by ln n to the p, is convergent for any p greater than 1. So what we're going to use for this is the integral test. So what does the integral test say? So the integral test says, think of your terms in your series as a function f of x evaluated at n. So in our case, this is 1 divided by x times ln x to the p. And then we consider the integral from 2 to infinity of f of x dx. What the integral test tells us is that if this improper integral converges, then the series converges. Okay. So this integral is equal to the limit as t tends to infinity of the integral from 2 to t of 1 over x ln x to the p dx. And to evaluate this, we're going to use a substitution. So our substitution is u equals ln x. So du is equal to 1 over x dx. So this is equal to the limit as t tends to infinity of the integral from ln 2 to ln t of, so our 1 over x and our dx give us a du, and the ln x gives us u to the p. So this is the limit as t tends to infinity of u to the 1 minus p divided by 1 minus p, evaluated at ln 2 and ln t. And so note here, in order to calculate this, we use the fact that p was greater than 1. Okay. So obviously this formula does not hold if p was equal to 1. Okay, but we're told in the question that p is bigger than 1, so it's okay to do that. So this is the limit as t tends to infinity of ln t to the 1 minus p divided by 1 minus p minus ln 2 to the 1 minus p divided by 1 minus p. And again, we use the fact that p is greater than 1. So as t tends to infinity, ln t tends to infinity, but we're raising it to the power 1 minus p. That's a negative power, okay, since p is greater than 1. So this gives us 0 minus, or let's write it as plus, ln 2 to the 1 minus p times by p minus 1. Okay, and so again, we're using the fact that p is greater than 1. So, hence the integral converges. So therefore, by the integral test, the series converges. Okay, so let's move on. And we move on to our penultimate question here, and our last question about series. And what we're going to discuss in this penultimate question is Taylor series. Okay, so Taylor series were pretty much the last topic that you saw in lectures. So I'm going to go through this relatively quickly. So in this question here, we're asked to first define the Taylor series of a function f at a. So let me remind you, this is the sum from n equals 0 to infinity of the nth derivative of f at a divided by n factorial times by x minus a to the n. So this is section 11.10 of the material. So that's the definition of the Taylor series, and then in the second part of this question we're asked to compute the Taylor series of the function f of x equals cosine 3x at a equals centered at the point a equals pi by 2. So what do we need to do? We need to calculate values of f and its derivatives at pi by 2. So first of all, f of x is cosine 3x. So therefore, f of pi by 2 is cosine of 3 pi by 2, which is equal to 0. F primed of x is negative 3 sine 3x. So therefore, f primed of pi by 2 is equal to negative 3 times sine 3 pi by 2. So that's equal to 3. F double primed of f is equal to negative 9 cosine 3x. So f double primed of pi by 2 is again equal to 0. F triple primed of x is equal to 27 sine 3x. So f triple primed of pi by 2 is equal to negative 27, and so forth. And so what we do now is we try and work out a general formula for the nth derivative. And so in general, what we see here is that, first of all, the even derivatives are all 0. Okay? So the even derivatives are all going to reduce to some constant times by cosine of 3 pi by 2, which is always 0. Okay? So here's f, here's the second derivative, differentiate twice, I get cosine 3x times by a constant again. So the even derivatives are all 0. The odd derivatives, well, there are two things. So first of all, we multiply by 3 each time we take a derivative. So my constant is going to be 3 to the 2n plus 1 for the 2n plus 1th derivative. But my sign is changing. And it turns out the right formula for the sign is negative 1 to the n. How do I know this is the right thing? Well, I could formally prove it by induction. I'm not going to do this. Let's just do a little check. So if we go back to here, let's check. This is the case where n is equal to 0. So I get 3 to the 0 plus 1 times negative 1 to the 0, which is equal to 3, which is correct. And here, this is when n is equal to 1. And my formula tells me I should have 3 to the 2 plus 1 times negative 1, which is negative 27, which is what I have, which is correct. And from that, I'm going to say that this is the correct formula for the 2n plus 1 derivative. And if you wanted to prove this formally, you could just prove it by induction. So with this in hand, the Taylor series is, so I only need to sum over the odd terms. Okay. We know that all the even derivatives are 0. So I just sum over the odd terms. So the first thing I have is the 2n plus 1th derivative, which I worked out was 3 to the 2n plus 1 times negative 1 to the n. Now, using my formula for my Taylor series, I have to divide by the appropriate factorial. So that's 2n plus 1 factorial, because I'm summing over the odd terms. And then I multiply by x minus a. So a is pi by 2 in this case. And because I'm considering the 2n plus 1th term, I have the 2n plus 1th power here. And that is my Taylor series. Okay, so to take away from this question, if you're asked to calculate a Taylor series, you need to calculate the derivatives of your function, generally find some rule for your derivatives, such as this, and then it's just plugging that into the general formula for the Taylor series, which is given by this expression here. Okay, so we are very nearly done. One final and mercifully short question to conclude things. Just to remember that we're going to have questions from all over the course in the final, although it would be primarily based on what we've seen since the second midterm. But nevertheless, we may go back to questions about approximation of integrals. And that's exactly what this question is about. So this question says, you take the function y equals f of x here, which I'm going to redraw. And you've decided that you want to approximate this using a series approximation based on 4 intervals. And let's just assume that these are the points 0, 1, 2, 3, and 4. And you're asked to say whether you should use the right-hand approximation R4 or the trapezoidal rule T4. Which one would you consider using? So, first of all, let's draw the right-hand approximation. So the right-hand approximation, you sum up these rectangles here. And that gives you your approximation to your integral. So we have 4 subdivisions here, and our total area is just the sum of these 4 integrals. That gives us our right-hand approximation. If we were at its right hand, because we evaluate the function at the right endpoint of the intervals here. If we evaluate it at the left endpoint, then it would be the left-hand approximation. And then we're asked to compare this with the trapezoidal rule. So what do we do in the trapezoidal rule? We approximate the area under the curve by a trapezoid in each subinterval. So here are my trapezoids. So the trapezoid, I should say, so a trapezoid is defined by 4 points. So in general, it's the endpoints in the interval here, and then the function values at the endpoints. Okay. So having drawn this here, it should now become immediately clear that the rule that we're going to want to use is the trapezoid. And this will be more accurate. So in this case, this just follows just by inspecting the curve that we're wanting to approximate. Okay, so that concludes the this final review class. For those of you who've made it all the way through this, congratulations. Congratulations on completing the course. Make sure you practice and study hard for the final exam. It's a very good idea to take these questions or similar questions and practice solving them under time conditions. And it just remains to say best of luck, and this is the end of Math 152 Spring 2020. Okay, thank you very much. Bye.